Hello, my name is Casey Loomis, and in this video I will describe what a convolutional neural network is and go through a code example where I describe how it works. If there are any errors or discrepancy in my explanation, please let me know in the comments. I'm very interested in making sure the information presented is accurate. If there is anything unclear about the concepts, please let me know in the comments, and I will do research and try and respond to it. It should be noted that it isn't important to have an accurate understanding of what the network layers are doing if you just intend to use the network for the purpose it was intended. As long as you put in the right kinds of input, you will get the correct results. But if you plan to use inputs that are different from the kind of images the network was intended to evaluate, then results might not be correct. This is why it's so important that the information in the video is correct. Despite this, only a general understanding of what the network layers are doing is required, because all the math and other complexity, such as weights, is hidden from view. So don't worry too much if you don't understand everything about the neural network layers. The math used in the convolutional neural network, such as the dot product and other various math functions, won't be discussed in detail because 1. They are applied for general purpose, and 2. They are done out of view with the express intent of you using the code without concern for how it works. I will just note where the math is used. There are several health applications for convolutional neural networks because most health information can be presented as various image scans such as MRIs. With that said, let's get started. A convolutional neural network is commonly used to classify images. The way this classification works is by making several versions of the image with exaggerated features. Using what's called a kernel or filter, the different versions of the picture are simplified further, using max pooling for example, and then evaluated in the hopes of properly classifying it. This process happens using network layers. The input of each layer in the network is the output of the previous network layer. As the image moves through different layers, the features are exaggerated and it is classified. Here is an overview of how that is done. To a computer, an image is just a grid of numbers, and each number represents a color. A much smaller grid of numbers, called a kernel, is placed over the image, and it is used as a filter that will change the image in some way. As the filter moves over the image left to right and top to bottom, a computation called a dot product is done, and a new image is created which hopefully exaggerates a feature of the original image in some way. The amount of space the filter moves right or down is 1 usually. The exaggeration is usually unrecognizable to us, but hopefully the network will be able to make use of it. The new image is called an activation map. As a result of this process, the activation map may be smaller than the original image. We will be putting a padding of zeros around the image and starting at the zero's edge, so that our activation map is the same size as our original image. Several activation maps are created for an image by using different filters, one per activation map. Some of the activation maps, because of the filters used, might outline edges of the objects, like heads or hands. Repeating the process on the activation map instead of the original image, which creates yet another activation map, outlines the edges of edges, which might possibly reveal details inside the object, such as eyes or noses on heads or fingernails on fingers. The collection of filters used on one image will be the same collection of filters that are used on every other image. New filters are not created for every input image. During training, each image from the training set will be processed through the network. A number called a weight will be associated with the filters that process an image. This weight will be increased or decreased depending on whether it leads to the successful classification of an image. That way, if the exact image were to be processed through the network based on the weights, it would be correctly classified. This process is called backpropagation, and we'll discuss that concept later. It is important to note that backpropagation requires that test data already be correctly labeled. There is no way to know what filters will exaggerate which features best, so they are initially created at random and in high volume. Several hundred activation maps can be created for each image this way. It is often difficult to visualize activation maps, but they only need to distinctly identify aspects of images. The activation maps are then generalized further using max pooling, so that only the most distinct features of each image remain. These max pooled images are much smaller than activation maps. Evaluating all of the max pooled image data related to the original image will hopefully help to classify it. Now let's look at a Python code example. In this example, we determine the emotional state of people based on their facial expression. The original code was provided by Kaggle.com. I had to make small modifications for the code to work with the newer version of Python. The updated lines of code is written in blue. The original line of code is written in green and commented out. The exact code change made is circled in red. The code is organized in blocks that have input labels, followed by numbers on the left side. Below the code blocks is the output of that block. Input block 1 imports 3 libraries, gets all the files located in the folder Kaggle input, and using a for loop displays all the files in that folder. The output shows that there are 4 files in that folder. Input block 2 imports several Python-specific libraries needed for the deep convolutional neural network. Input block 3 loads or reads the input file for 2013 CSV, which is a file displayed in the first input block. The first few rows of data in that file are outputted using the head function. The image data is stored in the pixel column, with each pixel value being represented by a number, and every pixel being separated by a space. One piece of data that isn't told to us is that the images are also perfect squares, so they have the same height and width. This will be important later. Block 4 displays only the unique values from the emotion column. Block 5 creates labels for the unique values of the emotion column and counts the total occurrences of each value in the emotion column. Block 6 displays the total occurrences of each value in the emotion column as a bar chart. Notice that most of the data is either 3, happy, 4, sad, or 6, neutral. Block 7 takes the square root of the number of pixels in the first image. This gives us the height and width because we know that each of the images is a perfect square. For example, an image with 25 pixels will have a height and width of 5. In this case, the height and width of our image is 48. Block 8 says that for each emotion there are 7, displays 7 examples. Block 9 counts the total occurrences of the 3 interested emotions, 3 happy, 4 sad, 6 neutral. Block 10 formats the image data into actual images. Note the 48 in the reshape function. Because the pictures are grayscaled and not color, the last parameter of the reshape function is 1. If the image were color, the last parameter would be 3, for the colors red, green, and blue. Block 11 creates the labels for the image data. Block 12 maps the emotions 3 happy, 4 sad, 6 neutral with 0, 1, and 2 respectively. Block 13 splits the data into training and validation, specifically setting aside 10% of the data for training. The random state parameter determines the randomness of your splits. Any positive number can be used, and I don't know why 42 is used except that it's a reference to The Hitchhiker's Guide to the Galaxy by Douglas Adams. The line below train test split displays the shape of the data outputted by train test split. Block 14 deletes unneeded variables. In block 15, the data sets are divided by 255 because the images are stored in 8-bit integers which have a value between 0 and 255, and we'd like them to be floats in the range 0 to 1. The computer likes these numbers better. Block 16 sequentially adds parts of the network onto each other, one layer at a time. After all the layers are created, the convolutional neural network is ready to process data and each image is evaluated. Note that the top of this block defines a function called buildNet, which has an input parameter optim. The optim parameter will be used later in the compile function to set the optimization style. This is the point where we build our convolutional neural network. The first layer in the network is a convolutional layer. When we use convolutional layers, we are insisting that there is a relationship with the pixels surrounding any given pixel of an image. For example, all of the pixels that make up an eye are always above the pixels that make up a nose. To review, a kernel, also called a filter, is placed over the image, and as it moves over the image left to right and top to bottom, a dot product computation is performed and a new image called an activation map is created, which hopefully exaggerates a feature of the original image in some obvious way. Evaluating all the activation maps related to an image will hopefully help classify the image. The parameters used in the conv2d command set the characteristics of the convolutional layer. The filter parameter sets the number of kernels applied to each image. Each filter represents a feature detector that can identify various features in the input image, such as edges, corners, and texture. The kernel size parameter sets the height and width of each filter. Remember that these kernels are initially generated at random, so we don't know what they look like. Our image is 48 by 48, and the filter or kernel, in this case 5 by 5 size, will be placed over the image, and as it moves over the image, an activation map will be created. The amount of space that the filter moves, right or down, is 1 by default. The image shape parameter is only used on the first conv2d function. It defines the input image size. The activation parameter sets the function that will be used for the transformation of the nonlinear input. The image qualifies as nonlinear. Nonlinear functions help define relationships with data. The person who originally wrote this code felt that the best function to use was the ELU based on its characteristics. Other functions can be used. See the documentation for details. The padding parameter is used to manage an issue called lost pixels. The filter is applied to all elements of the image, but depending on the filter's starting position, it passes over the center of the image more than the outer corner. The same attribute implements a way for the outer edge to be seen as much as the center by adding a padding of zeros around the image and placing the filter outside the bounds of the image. Other values for padding can be used, and they are defined in the documentation. The kernel initializer parameter sets the way that the filter weights will be initialized. Each input to a convolutional layer has an associated weight to it. During backpropagation, the weights are adjusted to favor the correct answer. This means that during the training stage, the filter that successfully classifies an image will be given a higher weight over time. This is what gives the network the ability to predict after the training stage. The batch normalization function is run between most of the network layers. Batch normalization adjusts the data so that the elements are not too different from the majority of data. This makes the network easier to train because it limits the values that it's looking for and because the values are closer together. This also reduces processing time. After that, an additional convolutional layer and batch normalization function are added to the network. I will describe why that was added to the network shortly. For now, I want to focus on the max pooling layer, which follows that. Recall that the max pooling saves only the highest values in areas of the activation map, and that is how we extract only the most dominant features of the image. Only those values will be carried forward. The parameters used in the max pooling 2D command set the characteristics of the max pooling. There are other parameters besides pooling size, but this program doesn't change any of their default values, so they aren't used, and they are defined in the documentation if you're interested. The pooling size parameter sets the height and width of the kernel. It moves across the activation map from left to right and top to bottom. Unlike the convolutional layers kernel, it moves to the right at the rate of its width and down by the rate of its height. In our case, the results of using max pool will create output half the size of our input. So far, we've created 2 convolutional layers in the network. Each layer consists of 64 filters which go back to that layer's input. So the first layer has 64 filters that go back to a single input. The first layer's output is the second layer's input. So each of the second layer's 64 inputs connects to the first layer's outputs, of which there are also 64. The max pooling layer is not illustrated in this diagram because there are no weights associated with them. Where the filters of the first layer find edges and sides from the original image, the second layer finds combinations of edges and sides from the activation maps of the first layer. For example, in this way, the first layer can identify silhouettes, and the second layer can identify details in the silhouettes, such as eyes and noses. If the images are simple and only consist of edges and sides, like letters and numbers, then only one convolutional layer is needed. If the image is more complex, and that complexity matters, like with faces, then stacking more convolutional layers will be needed. The more complexity that the network can see, the harder it will be for it to generalize the pictures into categories. This problem is referred to as overfitting. To address the problem of overfitting, a dropout function or layer is used to add variation to the training data by randomly switching some percentage of the nodes of the network off. When talking about networks in general terms, our filters are referred to as nodes. A node is a part of a network that takes input, creates output, or both. The first parameter of the dropout function is the percentage of nodes to turn off at any given time. In our case, that's 40%. When the nodes are switched off, the incoming and outgoing connections to those nodes are also switched off. That means that the image will not have certain filters applied to them during the training stage. This will make the set of max pool data associated with any image unpredictable from a training perspective. After this, another pattern of layers and functions are added to each node in the network that is not switched off, just like before, following the pattern of convolutional layer, batch normalization, convolutional layer, batch normalization, max pooling, and dropout. The difference is that this time the convolutional layer's filters attribute value is 128 instead of 64, and the kernel size attribute value is 3 by 3 instead of 5 by 5. As the kernel size gets smaller, the resulting output becomes more similar. So more filters are needed in order to emphasize differences. The kernel size and filter size is also changed to add variation to the training. This pattern of layers is added to our existing network in the order and manner it was called. Finally, another pattern of layers and functions are added to the network just like before, following the pattern of convolutional layer, batch normalization, convolutional layer, batch normalization, max pooling, and dropout. The difference is that this time the convolutional layer's filters attribute is 256 instead of 128, and the kernel size attribute value is again at 3 by 3. This adds more filters to the network to be trained. This pattern of layers is also added to our network, similar to before. A flattened layer converts all of the data related to the image into a single object. This is done by taking all the two-dimensional arrays of pooling feature maps and turning them into a single long, continuous string, similar to how our initial input image was stored in the pixel column, except there is no space character between the image pixel data. The in our network diagram represents the total size of the string, which is an unknown number. Because of dropout, we don't know how many filters were applied, so we're not sure about the total size of this string. Everything done up to this point is to gather the kind of information needed to classify the image. Everything after this point is meant to help predict the class of the image using the information already gathered. To do this, we create a dense layer. A dense layer is created by connecting every element of the flattened layer to a set number of nodes. In our case, 128. That's why the dense layer is also referred to as a fully connected layer. The dense layer takes the dot product of its inputs and their representative weights. By default, the weights are set to Glorot uniform, just like the convolutional layer. You can read more about that in the documentation, but the important thing is that the weights are created and updated automatically during backpropagation. During backpropagation, both dense layers and convolutional layers weights gets updated. Dense layers are updated to help the network classify images. Convolutional layers weights gets updated to let the network learn what features or filters are relevant. Unlike the convolutional layer, the dense layer loses the relationship that a pixel has with its surrounding neighbors because of the high number of connections. Where the convolutional layer knows that all of the pixels which make up an eye are always above the pixels that make up a nose, the dense layer must determine if the eyes are there and if they're above the nose. The first parameter of the dense function is called units, and it is set to the number of nodes that the elements of the flattened layer will be connected to. The number of outputs will also be the same as the unit parameter because of the kind of calculation done. The units parameter represents the attributes that the network needs to evaluate in order to make an accurate prediction. A higher number allows the network to learn more complex things. The higher the number, the more attributes an image will need to possess in order to be considered a match. If a network is trained using too many attributes, then it will result in overfitting. Generally, you want to start with a small number and slowly increase it until the accuracy stops improving. This number is a total guess. The activation and kernel initializer parameter in the dense layer does the same thing as the convolutional layer parameter of the same name. There are other parameters available, and they are defined in the documentation. The dense layer is followed by batch normalization and dropout, which have been described above. Another dense layer is created, but this time the value of the first parameter, num classes, is 3, and the parameter activation is set to softmax. The num classes is for the 3 emotion classifications we're interested in: happy, sad, and neutral. Softmax is a function that makes sure the output is only within the desired classification. Softmax makes sure that our prediction is a percentage, or from 0 to 1, adding up to 1, or 100%, between our 3 possibilities. Our dense layers were created in pairs because we created our convolutional layers in pairs. Remember that our convolutional layers were created in pairs so that we could detect edges of edges. The last step to creating the network is to compile it. The loss parameter is short for cross-entropy loss function. The parameter defines what kind of classification technique will be done. Each function does some kind of backpropagation. To review, that means we're using the answer to determine the correct steps to get to that answer. The loss function is trying to minimize the difference between the actual and predicted ranges of the different classes. Different functions can be used, and they are defined in the documentation. The important thing is that you know that options exist so you can determine if you want to use them. The metrics parameter sets the kind of information that will be tracked as the network runs. For example, Accuracy calculates how often predictions equal the labels. Different values can be used and they're defined in the documentation. The optimizer parameter has the value of the input parameter of the buildNet function. Recall that this will allow us to set the optimization style when the buildNet function is called. There are other parameters available, and they are defined in the documentation. After the compile function is run, the summary function is run. Summary counts the total number of parameters in the network. This is useful in determining if the network is parameter efficient compared to other networks. Finally, the function buildNet returns the network object that was created. In block 17, the early stopping function sets the condition that indicates the network has stopped improving. The monitor parameter sets the metric to be monitored, for example, value loss or value accuracy. The min delta parameter sets the minimum change in the monitoring metric to be considered as an improvement. The patience parameter sets the minimum number of epochs or training cycles with no improvement that must occur in order for the training to stop. The verbose parameter value can be either 0 or 1, with 1 representing true and 0 representing false. When set to true, messages will be displayed when the callback takes action. The restore best weights parameter sets whether to restore modal weights from the epoch with the best value of the monitoring metric. If false, the modal weights obtained at the last step of training are used. The reduce LR on plateau function sets the behavior of the network when it stops improving. The monitoring, patience, and verbose parameters function just like the early stopping function parameters with the same name. The factor parameter sets the factor by which the learning rate will be reduced. The min LR parameter sets the lower bound of the learning rate. In block 18, the ImageDataGenerator function is used. It runs through the images and applies random transformations to them so that the network never sees the exact same image twice during training. The rotation range parameter is a value in degrees from 0 to 180, a range in which to randomly rotate the pictures. The width shift and the height shift parameter are ranges as a fraction of total width and height, within which to randomly transform pictures vertically or horizontally. The shear range parameter is for randomly applying shear transformations. The zoom range parameter is for randomly zooming inside pictures. The horizontal flip parameter is used for randomly flipping half of the images horizontally. Other parameters are available, and they are defined in the documentation. After the ImageDataGenerator function is initialized, it is fit into the training data. The batch size parameter defines the total number of images that will be processed at any given time, and the epoch variable defines the number of training cycles. The buildNet function is called with the input parameter optims at index 1 or item 2, which resolves to the function optimizers.atom with the input parameter of 0.001. The input parameter for the function atoms being set as the learning rate. Once the buildNet function is called and given its optimizer input function parameter, it returns the network object. Now the model fit function can be called because all of the input parameters it needs is present. This will allow us to process the training data. Because of my computer's limitations, I had to limit the variable steps per epoch to 50 and the variable epoch to 30 and completely remove the feature use multiprocessing. In block 20, the training results are saved. In block 21, a line chart is created that represents the accuracy and training loss of the training and validation data over time. In block 22, a violin chart is created that represents the accuracy and training loss of the training and validation data over time. Block 23 calculates one of the variables needed to make the confusion matrix chart, y hat valid. In block 24, the confusion matrix chart is created that represents the accuracy of the network's ability to predict emotions by facial expression. It uses the variable y_valid. Ideally, the darkest colors should be in the diagonal, starting from the upper left corner and moving to the lower right corner. My confusion matrix does not reflect this because I had to limit the variable values of the model.fit function due to my computer's performance. Block 25 maps the emotions of interest with their corresponding numbers. Block 26 selects 9 sad images at random, followed by 9 neutral images at random, and displays their predicted values respectively. The output is displayed here. Many of the steps involved in creating the network, such as batch normalization, dropout, and ImageDataGenerator, prevent overfitting, which again is a problem where the network can only classify data that it was trained with, but not on new data. Creating multiple instances of the same layer with different parameters helps to introduce variation into the network, which also prevents overfitting. In this video, I described what a convolutional neural network was and used a code example to describe how it works. If you liked the video or found it useful, please add a like. Any comments or questions about the content would be appreciated. Again, if there are any errors or discrepancies in the explanations, please let me know in the comments. Thank you for watching.